Hello everyone, welcome to the lecture number 6. In this lecture, we'll talk about the concept of angular momentum. So when a body of mass m is moving in a straight line with velocity v, the momentum associated with this translational motion is called the linear momentum. But when this body of mass m is rotating with respect to one particular axis, the momentum associated with this rotational motion is called the angular momentum. So this is a motion which is called translational motion. Translational case, this is a rotational case. In the case of translational motion, what factor causes this translational motion? It is called force. Force causes this motion. And in the case of rotation or in the case of angular momentum, the similar or equivalent quantity that is associated with this kind of motion is torque. So from Newton's second law, you know that when there is a momentum change or the linear momentum change, force is associated with that kind of motion. So in the case of rotational motion, when angular momentum changes, then torque is associated with that kind of motion, rotational motion. So torque is a quantity that is associated with the rotational motion and force which is associated with the translational motion. And torque changes the angular momentum of the body and force changes the linear momentum of the body. Force is called linear momentum change rate. Similarly, torque is also called angular momentum change rate. Now we will not go there. First we will see what is angular momentum. So before going there, we know what is torque. Torque is moment of force. Moment of force. Similarly, the rotational case, angular momentum, it is called L. It is moment of momentum. Moment of momentum. So torque is R cross F. What is R? The point of application of force, direction vector, cross F. Similarly, for a particular body, if it is moving with respect to one particular axis, if the distance vector of that particular point mass is r, and if it is moving with velocity v, what it is? Momentum or linear momentum mv, but we will write mv vector. Moment of that is r cross mv. That is called angular momentum. See, it is a cross product. So angular momentum is also a vector quantity, just like the torque. Angular momentum is also a vector quantity. Now let's see in detail. Now suppose our axis is outward. Suppose z axis is outward and x and y axis is like this. Z axis is outward and one mass, point mass of mass m is moving with velocity v in this direction. Now at this instant, the distance vector of that point mass is r and it is going with the velocity v in this direction. Then what I told, angular momentum is just the moment of the momentum, means we will just do r cross m v. Now if we extend this r vector like this, so this is the direction of the r vector, and between r and v, if the angle is theta, then we can write that m will come outside because it is a scalar quantity. So it is just r cross v we can write. And what is the cross product of these two vectors? If the angle between them is theta, then you can write RV sin theta. That is the magnitude of the angular momentum. Now, what is the direction of that angular momentum? See, this is the R vector. This is the V vector. So their cross product means R cross V. It is pointing outward of the board. So outward of the board is the Z axis. So we can multiply this magnitude with the unit vector in the Z axis, and we can write K cap. So angular momentum we got, it is MRV or MVR sin theta into K cap in this case. So this is the angular momentum vector formula. Now say at given instant the position vector of this particular mass is r and its coordinate is x comma y. So we can write r as x I cap plus y j cap, and its velocity v, as it is moving in 2D plane, in this plane only it is moving, v is vxi plus vyj. Vx and vy are the velocities in the x direction, the y direction, so we can write velocity vector like this. So what is the value of angular momentum? L. We can directly do the cross product, r cross b. So we'll write I, j, k. We'll write x, y, 0, vx, vy, 0. So we'll do the cross product. So r cross v will do. So k into x vy minus y vx. So we'll write m x vy minus y vx into k cap. That you can write L. That is the angular momentum if the particle is moving in xy plane or two-dimensional plane. It is only having k component of the angular momentum. So we can write Lz also k cap as m x vy minus y vx k cap. So we can write Lz or the angular momentum in the z direction, that is m x vy minus y vx. Now let us solve a simple problem of projectile motion. One particle of mass m is projected at an angle theta with the x-axis. So it is going to have this kind of parabolic path. At the topmost point, find out angular momentum. If it is projected with velocity v naught in this direction. See, at the top point, it is only having one component of velocity. See, v naught, we can resolve in two components. One is v naught cos theta, which is in the horizontal direction, and v naught sin theta, which is in the vertical direction. The vertical direction component is slowly reducing towards the top point. At the top point, the y direction velocity is going to be 0. There will be only having v naught cos theta velocity at the top point. Now what is going to be the angular momentum with respect to this origin? So see, this v naught cos theta component is only creating the angular momentum at the topmost point. Now we can do one thing, just like the torque, if we want to find out m r cross v, that means r is basically the position vector of this particular point r, and v is in this direction. So basically this is the direction of r vector. See, if it is having two components, then we have to consider this component of velocity as well. But right now it is only having one component in this direction. So we can directly draw one perpendicular on this velocity from this origin. If we draw one perpendicular to the velocity vector, we are going to get this distance. And this distance is the maximum height, basically, h max. So the angular momentum L will be perpendicular distance multiplied by this vector v naught cos theta multiplied by mass or the momentum. So m h max into v naught cos theta, and the direction of it is trying to rotate in this clockwise direction, so it is going inward. So you can write minus k cap. So h max is, you know, v square sin square theta by 2g into v naught cos theta. So it is becoming m v naught cube sin square theta into cos theta by 2g. That is the angular momentum vector. If we write, it is minus k. That is one method, method 1. Method 1 is we have to draw one perpendicular to the momentum vector or the velocity vector, and we can multiply the perpendicular distance with that momentum, we will get the angular momentum. Now another method is, as you know, angular momentum is r cross v. You can write what is the r vector at the topmost point. When the particle is at the topmost point, what is the r vector? See, this is the range, so this is the half range, r by 2. So you can write, so this position vector, you can write r by 2 I cap plus h max j cap. So this position x is r by 2 and the y position is h max, this point. And velocity vector at the topmost point, we can write v naught cos theta I cap. And the momentum vector is basically, then it will be going to be m v naught cos theta I cap. That also we can write, but it is not required. We are using this formula, so it is not required. So L will write as m r cross v, means we will just write r by 2 I plus h max j cross v. V means v naught cos theta into I cap. So see, I cross I will be 0. We will be only left with m h max v naught cos theta only into j cross I is minus k. So similar kind of expression we are getting, v naught square sin square theta by 2g v naught cos theta, that is eventually we are getting m v naught cube sin square theta cos theta by 2g minus k cap. That is the method 2. Now let's see the extension of the first problem, problem number 2. Same problem, I am telling you to find out what will be the angular momentum at the final point or the point of landing with respect to the origin. So you know, in the projectile motion is symmetrical with respect to the maximum height point, or with respect to the maximum height. If I draw a line like this, the entire projectile motion is symmetrical both sides, but in opposite direction. Just like if at this point from the maximum height line, or x equal to r by 2, or the half range line, straight line, if at distance x to the left hand side, if the velocity is suppose v1 in this direction, at distance x from the maximum height line to the right hand side of the maximum height line, it will be same velocity but in opposite direction, downward direction. So with respect to this maximum height line or the half range line, this point of projection and the point of landing is at the same distance, both sides. So here if the velocity is upward v0, here it will be downward with velocity v0. That means if it is projected with a velocity v0 at an angle theta with the horizontal upward, it will land with same velocity making an angle theta with the x-axis. Now in order to find out the angular momentum, what I can do is I can resolve this velocity into two components. One is this velocity, that is of course v0 sine theta, and this velocity is v0 cos theta. It is constant throughout the motion of the projectile. It is v0 cos theta. Now see, v0 cos theta vector is collinear, or it, if I extend this, it is intersecting the origin. So with respect to origin, there is no distance vector or there is no perpendicular line we can draw on this v0 cos theta velocity component. Now if I draw one perpendicular on this v0 sin theta component of velocity, we will get that range r is a distance to this point, and that is the perpendicular distance to the v0 sin theta. So v0 cos theta we cannot draw any perpendicular. So there will be only angular momentum generated due to this component of the velocity. We can solve it by the method of vector also, but firstly we'll solve with this method. We'll draw a perpendicular on these two velocities and we'll find out what is the angular momentum. See, the angular momentum vector, it is trying to rotate with respect to this origin in this direction or clockwise direction. It is directed inward. So the direction of the angular momentum is of course minus k cap direction. Now angular momentum is, we know, if we draw a perpendicular on this velocity, we'll get m multiplication of the distance into that velocity v0 sin theta, or we can write, or we can multiply also the distance with the momentum vector. Due to this momentum only it is creating the angular momentum, and the other momentum is m v0 cos theta. Due to that there is no angular momentum is created. So this is the angular momentum. So what is r? You know the range formula, v0 square sine 2 theta by g into m v0 sin theta multiplied with the direction vector, unit vector. So we can write m v0 cube sine 2 theta sin theta by g minus k cap, that is the angular momentum. Now again we'll use another method, that is the vector method. So here also we can do it. So we can write the position vector of this particular point. At that point we have to calculate the angular momentum. So what is the position vector of this particular point? See, it is only having the x distance. So we can write the direction vector r cap is basically capital R, that is the range, into I cap. There is nothing in the y direction. So the coordinate of this point is r comma 0. And v vector we can write v0 cos theta I plus minus v0 sin theta into j, because it is directed towards the negative y direction. So we can always do this m r cross v, that is m r is, we'll write r I cap cross v0 cos theta I cap minus v0 sin theta j cap. see, due to this component, it is I cross I, that is why it is not creating any angular momentum. So this will be 0. So it is m v naught, only will multiply with I cross j. So m v naught r sin theta I cross j is k, and there is a minus initially. So it is the same expression we are getting, m v naught r sin theta, here also we are getting m v naught r sin theta into minus k, here also minus is there. So we will get the same answer eventually. I hope you understood. Now we will talk about the angular momentum for a distributed mass body or a rigid body. Let's see. Suppose this is a body which is rotating with respect to this axis. This is rotating with angular velocity of omega. Now this solid body is constituted of many small masses, dm, dm, dm everywhere. This direction also dm, dm. There are different distances from this axis. Let's say this dm is at r1, this dm is at r2, this dm is at r3. So we'll call it m1, m2, m3 till mn. We consider till mn, the distance vector is rn. Now what will be the angular momentum for m1 mass, which is at distance r1, rotating with respect to this axis with angular velocity of omega? You know, angular momentum or dl, small angular momentum for this small mass, it will be m1 r1 into v1. Now why I am writing r1 into v1 not r cross v? Because if I see it from the top, suppose this is the top view, this is the m1 mass, it is rotating with angular velocity omega. That velocity is related tangentially with the r vector or r1 vector for this particular particle. So on the concept of circular motion, you know that if one particle is rotating with respect to one axis with angular velocity of omega at distance r1, its velocity v1 will be basically r1 into omega, and this direction will be tangential to the distance vector. Tangential to the distance vector means the angle between r vector and v vector is 90 degree. So r cross v is basically rv only. We are writing. So we will write m1 r1 omega into r1. That is the velocity if it is rotating with angular velocity of omega with respect to this axis. So we can write that m1 r1 square into omega. That is small angular momentum dl for one mass m1. Now there are many masses, small masses, m1, m2, m3, mn. So total angular momentum for this solid body will be the sum of all individual angular momentums. So net angular momentum L will be the summation of all small angular momentums dln, or we can write dli from I equal to 1 to n. Now what is small angular momentum? What we have found out? We will write mi ri square into omega, I equal to 1 to n. Now omega for this solid body is constant because it is rotating with angular velocity of omega. Angular velocity is constant for all these masses. All these masses are rotating with respect to this axis with angular velocity of omega. So omega will come out of the summation. We will be only left with mi ri square. Now see, this part is the moment of inertia. Moment of inertia is summation of mass into the distance from the axis square. So we can write omega into I, or we will write I omega. That is equal to the total angular momentum. Now as we found out the value of the angular momentum is I omega, but I told that angular momentum is a vector quantity. So this is just the magnitude of the angular momentum. Then what is the direction of the angular momentum? What is the vector here? I is not a vector, I is a scalar quantity. Vector is omega only. So the angular momentum direction, it will be same as the direction of the angular velocity. So L will be I into omega vector. But in this case, it is only rotating with respect to one particular axis, suppose Z. So it will be only I into omega in that direction. I into omega, we'll write that. Lz equal to I into omega. Nothing else. That's it. Now one simple concept development. If one disk, circular disk having uniform mass density is rotating with respect to z axis with angular velocity of omega, what will be the angular momentum? So angular momentum will be multiplication of I and omega. Now I is, it is rotating with respect to the center and the axis is perpendicular to the plane of the circular disk. So what is I for this disk? M into r square by 2. So angular momentum associated with this disk is L vector, that is equal to m r square by 2 into omega into k cap, because k cap is the direction of the angular velocity. So this is the angular momentum associated when a disk is rotating with an angular velocity of omega. Now let us see another problem. This is a ring of mass m which is connected to its center via 3 small m mass rod of uniform density. Now what will be the angular momentum if this ring along with this rods are rotating with respect to z axis with velocity, angular velocity of omega? So L will be basically I into omega into the direction vector of the omega. Okay. Now I have to find out what is going to be the I. I will be the summation of the moment of inertia for the ring and these 3 rods. So ring, I ring plus I rods, but there are 3 rods, so we'll write 3 into I rods. So what is the moment of inertia for a ring of mass m and the radius r? I ring m into r square on. Now closely observe these 3 rods. These 3 rods are rotating with respect to their extreme end, and the length of these rods are r, the radius of the ring only. The mass is small m. So what is going to be the moment of inertia for one rod? M into r square by 3, or m into l square by 3. Here l equal to r, so we write m r into r square by 3. So total moment of inertia, total, that is I ring, that is m into r square plus 3 into I rod, that is m small m into r square by 3. So it is basically becoming m plus m into r square, that is the I total. So total angular momentum will be total moment of inertia multiplied with the angular velocity, and direction will be k cap, so it is vector. That is our answer. Now we learn about the conservation of angular momentum. So from the Newton's first law, you know that when no force is applied or no external force is applied, one moving body will continue to move with the same velocity. So if F is 0, it will not cause any momentum change. So momentum change d dt of mv or momentum change rate will be basically 0. So mv will be basically constant. Momentum will be constant. Now replace the term force in the Newton's first law with torque and replace the momentum in Newton's first law with the term angular momentum. So we can tell that when no torque is applied, one rotating body will continue to rotate with the same angular velocity. That means if torque is 0, torque is basically rate of change of angular momentum. Just like the force is the rate of change of momentum, the torque is the rate of change of angular momentum. So that means d dt of I omega, that is 0. If no torque is applied, the change of angular momentum will be 0. So you can write that I omega will be constant. That is the conservation of angular momentum. Now let's solve a problem with the concept of conservation of angular momentum. Suppose a disk is initially rotating with angular velocity of omega with respect to the z axis. Problem number, its radius is r, mass is m. Now one small insect of mass small m sits on this disk at distance 3r by 4. Then what will be the new angular velocity? We can solve it with the concept of conservation of angular momentum. See, no external torque is applied here. So if initially it is rotating with angular velocity of omega, then multiplication of I omega, that is the angular momentum initial angular momentum, that will be same as the final angular momentum. Let's say this velocity is becoming omega naught and new moment of inertia is becoming I naught with respect to this axis. So I naught omega naught will be final angular momentum. Final angular momentum. Now from the conservation of angular momentum, I omega will be equal to I naught into omega naught. So omega naught is I into omega by I naught. Due to the insect of mass small m sitting at distance 3r by 4, it will change the moment of inertia of this rotating body. Now the system will constitute not only with the disk, but it will also include the insect. Now what is the new moment of inertia? So before that we will find out what was the initial moment of inertia, that is the only disk was rotating. So moment of inertia was m into r square by 2. Now new moment of inertia is, the disk is there, mr square by 2 will be there, plus another moment of inertia that is contributed by the insect of mass m. See, insect we can consider as a particle mass. So m mass is located at distance 3r by 4 from the axis of rotation. So we can write that mass into distance from the axis square. So new moment of inertia is becoming m r square by 2 plus 9 by 16 small m into r square. So new angular velocity will be, we'll put the values of I and I naught. I naught is m r square by 2 plus 9 by 16 into m r square. If we simplify it, we'll cancel r square, so it will be m by m plus 9 by 8 into m multiplied with omega. Now this is the new angular velocity. Now see, its angular velocity is reduced. This term at the denominator is higher than the term at the numerator. So this entire factor will be less than 1. So omega naught will be less than omega, that is for sure. So basically, due to the insect sitting on the disk at this position, it will reduce the angular velocity of this disk. And now if I have to maintain the same angular velocity, I need to apply external torque. But this is the question, this is the answer of this question.